Welcome to Empowered Learning. This is the third video in the video series for improper integrals. And so in this video, what we are going to do is evaluate improper integrals that we know that converge. So what this means is we know that we're going to get a numerical answer for these particular integrals. And we're going to be dealing with ones to where we can actually evaluate these improper integrals by hand. So this first example here just asks us to evaluate the improper integral of 1 over x squared plus 25 dx and evaluate that from 5 to infinity. So essentially this is a rational function, and this rational function has a horizontal asymptote at y equals 0. So just to kind of give you a visual on what this is actually trying to get you to do. From 5 to infinity, this rational function is going to look something like this. So let's say if I plug in a 5 here, this would be like 1 over 50. And this function is going to go like that. And we have a horizontal asymptote on the x-axis here, and it just keeps on going like this. And what we want to do is find the area under the curve of this particular function. Let me draw that in a different color here. So we want to find the area under the curve of this particular function from 5 to infinity. And the fact that we know that this improper integral is convergent means that we're actually going to be able to find a value to represent the area under the curve from x equals 5 all the way to infinity. Okay, so we see here that ignoring the limits of integration here, this is just a simple integration problem where we see here that our integrand can be rewritten as 1 divided by x squared plus 5 squared. And if we do some algebraic manipulation here, what we'll see is that we could look at this integrand here as just 1/5 times 5 over x squared plus 25. And the 5 divided by x squared over 25 will just end up being, when we take the antiderivative of that, it will be arctan, or tangent inverse, of 1/5 x plus c. Okay. So because of that, and we have this extra 1/5 that's out here, then that means that the actual antiderivative of this integrand on its own is just going to be 1/5 of that. Okay. So we see here that to evaluate this improper integral, we need to take the limit as the upper limit goes to infinity, and we just replace infinity with a b there. And here we evaluate this definite integral in here, and we already know what that ends up looking like. It's going to be arctan of 1/5 x evaluated from 5 to b. And so we just go in, plug in b everywhere where we see x for the first term, and do the same thing, plug in 5. We note here that, of course, arctan, or tangent inverse of 1, is just going to be pi over 4 radians. For those of you that think in degrees, that'll be 45 degrees. And of course, tangent inverse of b over 5 will just have to remain tangent inverse of b over 5 for now. So we're here, and we see that once we write this way, the only thing that's left to do now is to evaluate this expression using our limit operator. So here we would have to put infinity in place of b, and we note here that arctan, or tangent inverse, as the x values go to infinity, the y values are approaching pi over 2, and that's because of how the graph of arctan looks. And so then from that, once we know that, we just replace tangent inverse of infinity with pi over 2. We already know tangent inverse of 1 is pi over 4. and we see that we end up getting the answer of pi over 20. And so note here that my explanation for how we know, first of all, that the antiderivative of this is just going to be 1 over whatever this value is times tangent inverse of x divided by a plus c. I kind of go through all that here. The more important thing here is, how did I know that tangent inverse of pi over, of infinity is going to be pi over 2? And again, this is what the graph of arctan or tangent inverse looks like. And as you see, as x goes to infinity, the y values approach this horizontal asymptote here. Okay, so as far as the other stuff I have written down here, all that I'm really doing here is sort of going back to first year calculus and showing how if we were to define arctan or tangent inverse of x divided by a as some angle named theta, if I were to of course do the tangent of both sides and end up with what I see here, and then take the derivative of both sides with respect to x, that I would have to do implicit differentiation to end up with what the derivative of arctan would end up being. Okay, so without trying to go through all the gory details in that, what I would see is that the derivative of arctan, or the derivative of theta with respect to x, would just end up being a divided by x squared plus a squared. Okay, and so if that's the case, then I know that if I was to take the same result and multiply it times 1 over a, what I'm saying here, then that means that I would have 1 over a times what I'm looking at here. And of course, those a's would reduce to 1, and I would essentially get what I had in the beginning as far as what my integrand was to be able to integrate. And so this lets me know, because of this result, that the antiderivative of 1 over a squared plus x squared, which is the same as 1 over x squared plus a squared, is just going to be 1 over a times tangent inverse of x divided by a plus some constant. Okay, so that was just some background info, just in case you were not familiar with how to take the antiderivative of what you saw there. All right, so let's move to the next example. All right, so for this next example, pretty much the same thing. We know that this particular improper integral will converge. We just need to figure out the value that it converges to. Now, how we know this is an improper integral is because here, if we were to actually plug in 196 down here, then of course we would have essentially 1 divided by 0. And so what this lets us know is that this particular function here either is, it's undefined because it has a vertical asymptote at x equals 196, or there's something else going on. More than likely, it either has an abrupt end of a domain, or it has a vertical asymptote there. Okay, we don't really care at this point what it is. What we do know is that because of the fact that 196 is not in the domain of the integrand, 1 divided by square root of 196 minus x, that we know it's an improper integral. And because of that, we're going to have to evaluate this with some care. So here we know that this 196 is the problem. So what we're going to do here is say we're going to take the limit as b approaches 196. And since this is the upper limit, we're going to approach it from the left-hand side. And we're just going to integrate from 0 to b of dx over square root of 196 minus x. Okay. Now, from this point, we see that in order to evaluate this definite integral that we have inside here, we are going to need to do the substitution rule. So let's go ahead and do that. So you see here, we will let u equal 196 minus x. And so this will imply here that du is equal to a minus dx, because the derivative of 196 is 0, derivative of negative x is just a negative 1. And so that means that minus du will be equal to dx. Okay. Dx. All right. So we also know here that our limits of integration are going from 0 to b. So I want to say u of 0 u of 0 is just 196. And of course, u of b is just going to be 196 minus b. Okay. And so with that being said, we will go ahead and use this information to be able to evaluate our integral now. So here we have limit as b approaches 196 from the left. And this will be, again, 0 to b. Let's try this again. 0 to b. And this will be minus du over square root of u. Okay. And here for these limits, it's supposed to be in terms of u here, so this should actually be 196 here. And this should be 196 minus b. So 196 minus b, like that. Okay. So now that we have that in place here, realize that b is going to be a number that is greater than 0. So that means that 196 minus b is a number smaller than 196. Okay? So I'm saying all that to say that these limits of integration here are opposite of how they need to be. Okay? So here, in order for us to fix that, we can put the 196 minus b down here and the 196 up here as the upper limit, and get rid of this minus sign here per our properties on integration. So I'm going to go ahead and do that now. So get rid of that. Go ahead and get rid of these parentheses here too. So this will be 196 minus b. This is 196. And we know that this understood 1 divided by square root of u here, that is the same as u raised to the negative 1/2. So that's actually what we're dealing with here. And so now all we need to do is just integrate what we have by taking the antiderivative of u raised to the negative 1/2 in terms of u. Simplifying that answer once we're done applying the net change theorem, and then evaluate the resulting expression, evaluate the limit of that as b approaches 196. So what I'm going to do here is kind of drop down right here, and we'll go ahead and pick back up, and I will do this in a different color. So let's choose, not that color. Yeah, let's choose this one. All right, so now we have limit as b approaches 196 from the left. The antiderivative of u raised to the negative 1/2 will be 2 times u raised to the positive 1/2. And that, of course, will be evaluated from 196 minus b to 196. And I'll change the way this grouping symbol looks. So we have limit as b approaches 196 from the left. And this will essentially just be 2 times and square root of u from 196 minus b to 196. And this will be 2 times square root of 196 minus 2 times 196 minus b. And of course, the square root of 196 is going to be 14. So that means that 2 times 14 is going to be 28. And let me scroll down here. This is going to be limit b approaches 196 from the left of 28 minus 2 times 196 minus b. And so now we just need to evaluate this expression. And essentially all we need to do is plug in 196 for b. And when we do that, you see that square root of all that ends up being 0. So our result here ends up being 28 at the end of the day. And so that will be what the actual area under the curve of this particular function would be from x equals 0 to x equals 196. So the final thing that we need to say is, of course, we already knew that this converged, but now we see why a particular integral converges, okay? Because it actually ends up equaling a real number here. All right, let's move to our next example. Okay, so for this example, we know that we could rewrite this here as the integral from -1 to 8 of x raised to the -1/3 dx. And notice here that because if we look at this denominator here, if I plug in 0 in for x, that would make me end up dividing something by 0. And since 0 is in between -1 and 8, we know that this is an improper integral because of that. Okay. So what this also tells us is that since 0 is a number in between -1 and -8, what we need to do is consider evaluating or splitting this integral up into 2 separate integrals here and making sure that both improper integrals will actually converge. Okay. And again, we know that this particular this integral here is going to converge because that's what we were told. So what this should lead us to believe here is that these 2 improper integrals that we're going to evaluate will both have to converge to some number. Okay. Now, to make life a little easier on us here, one thing that we want to note is that if we did the indefinite integral of 1 over the cube root of x, which we know could be rewritten this way. Then, of course, using the power rule for antiderivatives here, this would end up being x raised to the 2/3 over 2/3 plus some constant, which is just 3 over 2 x raised to the 2/3 plus some constant. And the main thing that we are concerned with here is this first term. So we know what the antiderivative of x raised to the negative 1/3 will be. And so we're going to use that to our advantage here to evaluate these improper integrals. So to do this, I am going to just write this as I1 plus I2, where, of course, I1 will be this first integral, and I2 will be the second integral, where both of them, again, are improper integrals. So let's go ahead and solve, or evaluate, rather, I1. All right, so we already know here that because this is an improper integral, we will have to rewrite this as limit as b approaches 0 from the left of -1 to b x raised to the -1/3 dx. Right, so limit as b approaches 0 from the left again. And so here we know that the antiderivative of x raised to the -1/3 will end up being 3 over 2 x raised to the 2/3, and this will be evaluated from -1 to b. Make this look different here. All right, so now from here, again, we just need to evaluate this expression here at b, and then minus, then at -1, and then we'll repeat the process for I2. So let's go ahead and finish this one up here. And on the next one, since we kind of know what the outcome is going to be, I'm going to skip some steps. We got limit. That's not working, so let me just move on to the next line. So that'll be limit as b approaches 0 from the left again. So it'll be 3 over 2. And we will have b raised to the 2/3. So this will be b raised to the 2/3 minus -1 raised to the 2/3. All right, and so we know that b raised to the 2/3 is the same thing as the cube root of b squared. So we can just leave that as is. This -1 raised to the 2/3 is the same as the cube root of -1 squared. And since -1 squared is 1, cube root of 1 is also 1. So all this is going to be limit as b approaches 0 from the left, 3/2 of, say, cube root of b squared here, minus 1. And of course, if we just plug in 0 here for b, whenever we evaluate the limit, then what we're going to see is that we have 3/2, 0 minus 1, which will give us a minus 3/2 here. All right, so that is what our improper integral I1 will end up being. Now for our improper integral I2, pretty much everything else is going to be the same except for where we start with the limits of integration here. So I'm going to purposely skip some steps, and I'm going to skip to I get to this particular point here. And I'm going to underline it. So I'm going to skip and start here because everything else is pretty much the same up until I get to that point. Of course, the limits of integration will be different. It will be going from 0 to 8 instead of from -1 to b. Well, sorry, I'm looking in the wrong spot here. This will be going from b to 8. Yeah, so I know I have to actually write it and change it here, but I wrote it and changed it at this point. But I'll have to at least do this step to rewrite it and change it, and then I'll just skip directly to here. All right, so let's go ahead and do that now. All right, so now we're going to evaluate I2, and that's just going to be the integral from 0 to 8 of x raised to the -1/3 dx, and that's going to be the same as limit as, and in this case, instead of writing a b, I'm going to write an a. Yep, so a is going to approach 0 from the right, and this will be an integral of a to 8 of this. And so now I'm going to go ahead and skip to this step right here. So we know this is going to be 3/2 integral here of a raised to the 2/3, which I'm just going to go ahead and rewrite that as cube root of a squared. Minus sorry, that's not right. So the upper limit here is 8. So this should be cube root of 8 squared, and then minus cube root of a squared. Yep. So that is what I'm trying to do there. And again, I'm doing this because we know that we have to take the antiderivative of the same function. It's just over different limits of integration. So instead of having a -1 and a b here, I'm going to have an a and an 8. So that means 8 would have to be plugged in first, and then in this case the a would have to be plugged in second. So that's what I have here. So from that, I'll go ahead and move on down here. So we have limit as a approaches 0 from the right. We know that 8 squared is 64, and the cube root of 64 is 4. Another way that we can do it is just split this up as cube root of 8 times cube root of 8. And since cube root of 8 is 2, we got 2 of those 2's multiplied together and you get 4. So either way, you'll end up getting 4 here. And then we'll do minus cube root of a squared. And here, if we let a go to 0, then that's just going to make that last term 0 there. And this will end up being 12/2, which is 6. And since I have to add these two together, I'm actually going to kind of be smart here and just leave the second answer in fraction form, or improper fraction form. And so now we see that, of course, all we need to do is just add these two up to be able to find out what our value for the improper integral is. And we see that if I add 12 over 2 to a minus 3 over 2, I'm going to get a positive 9 over 2. Okay? So all that is to basically say here, therefore, we do the integral from -1 to 8 of x raised to the -1/3 dx. That's just the same as I1 plus I2, which is a minus 3/2 plus 12/2, which is 9/2. And of course, we see here, because our result ends up being a real number, that our improper integral does indeed converge. All right, so let's move on to the next example. Okay, so for our final example, we're asked to evaluate the definite integral of 1 divided by square root of absolute value of 2x. And that will be evaluated from x equals -8 to x equals 2. And so here, what I've done to start off this particular problem is to sort of build what the function 1 divided by square root of absolute value of 2x would actually end up being. Note that the reason why this is an improper integral is because x equals 0 is not in the domain of this function. Because, of course, if I plug in 0 here, I would get something divided by 0, which we know is not legal. Okay? So what that tells us is that we are going to essentially have to split this up into two separate integrals, where the partition number is going to be at x equals 0. Okay? Now, according to definition of absolute value, I know that the absolute value of 2x would just be 2x for all non-negative values of x, and it'll be the minus of 2x for all negative values of x. So if I was to square root that, then of course I'm just square rooting. Okay, and again here, as long as x is non-negative, absolute value, absolute value of square root of absolute value of 2x would just be square root of 2x, and for all negative values of x, it will be square root of the negative of 2x. Now, if we did the reciprocal of that, then of course everything stays the same except for the fact that now notice that x equals 0 is definitely not in the domain of that function. Hence why we say that 1 over square root of absolute value of 2x when x is 0 is going to be undefined. And so that is what I was referring to up here. So here we're going to say that we know we have a vertical asymptote, which is a certain type of discontinuity at x equals 0. And that's the reason why this is going to be improper, which means we're going to have to do our fancy, limit notation as we evaluate this particular integral. So here we go ahead and set everything up. And let's go here. So we start here, and we know that 0 is the partition number that kind of is where our discontinuity is. So we're going to have to break this definite integral up into two separate ones. And of course, here we see that since 0 is the upper limit for this first improper integral, then we're using b, and it's going to be the lower limit for this second term. So of course we're using a, and I'm just using that convention to keep it consistent, so that you'll know what is what. You can use any letters that you want, but I like to use A for the lower limit and B for the higher limit. So we also see here that since this particular function, this square root of absolute value of 2x is going to be equal to this for all negative values of x, and same kind of thing holds true for all values of x that are non-negative, then here what we can say is that we're not going to look exactly at x equals 0. Okay, so we're just going to look when x is negative, when x is positive. So we split this up into two separate integrals here, and we're going to call this one let me get this drawn in the right place here. So we are going to call the integral on the inside of this I1 and the integral on the inside of that I2. Okay? And notice that this goes from -8 to b, and then from a to 2. And of course, in both of those cases, both b and a are approaching 0, just from opposite sides of that number. So with that being said, to evaluate the integral of both of these, we see that in order to do it, it's advantageous for us to go ahead and use the substitution rule. So we let w in this case equal -2x, and that means that dw is going to be a minus 2x, minus 2 dx, which means that the minus 1/2 dw is equal to dx. And we also go ahead and translate our limits of integration that are in terms of x to being in terms of w now. Okay, and here if I was to plug in a -8 into x here, a -8 times a -2 gives me a positive 16, so that's why you see that. And a b here, if I was to go ahead and plug in a b for x, that would just end up giving me a minus 2b if I did that. So that's where you get those new limits of integration from. So we go ahead and substitute what we have here for everything in terms of w. We go ahead and switch the limits of integration here from 16 to minus 2b to minus 2b to 16. And that's because we're assuming here that b is going to be a positive number. And so that means that this negative number will always be smaller than the positive number 16 here. So we do that, flip the limits of integration, multiply by -1, which gets rid of this minus sign here. And then rewrite 1 over square root of w as just w raised to the -1/2. Take the antiderivative, evaluate at 16 minus -2b, and you see that this is the outcome that we get for that. So that's the expression in terms of b. If we do the same exact thing, but do everything with the course substitution, let everything be written in terms of u, and let u be equal to 2x, then we see what all that is. Do translation of the limits of integration and work everything out similar to what we did above. You see that we end up getting basically square root of 4, which is 2, minus square root of 2a. And so now to finish up, all we have to do is evaluate the limit of this first expression as b approaches 0, limit of the second one as a approaches 0. And you see once we do all that, we end up getting 6 here. And so, of course, this corroborates the fact that this particular improper integral does converge. And we know it converges because, of course, it ends up equaling a real number, which again tells us that if we were trying to quantify the area under the curve of this function from x equals -8 to 2, we would be able to do it. All right, so with that said, this concludes the part 3 video for improper integrals. The next video that I will do will cover what's called the direct comparison theorems as well as the limit comparison theorem. And so these two theorems are used whenever either we don't want to or it's very difficult for us to actually evaluate the improper integral for a particular function by hand. And the goal here is not necessarily to figure out what the actual value of the improper integral actually is, if it is convergent. It's more so along the lines when we use these theorems to figure out whether the integral actually does converge or not. And in many instances, if you're going to be using these particular theorems, you're using it just to say, all right, well, if I'm going to go through the pain of actually finding what this particular value of this integral is, I need to know that I'm going to get an answer before I do it. And so that's really the purpose of those two theorems there. So I'll talk about that in the next video. Hope to see you there.